Hello everyone! In this mathematics and calculus tutorial, we explain how to correctly express complex numbers in the polar form. The main motivation for creating this video tutorial comes from the fact that we have observed that a number of students do not know how to correctly transform a rectangular form of a complex number to the polar form. Consequently, we created this tutorial in order to explain how to write the polar form of a complex number. As an illustration, in this tutorial we will solve these four problems. First, let us explain what is a polar form of a complex number, and let's derive an equation that will help us to transform the rectangular form to the polar form of a complex number. Let's start from scratch. In this video tutorial, a complex number will be represented by the letter z. And the complex number has the real part, denoted by a, and it has an imaginary part that multiplies the imaginary unit that's denoted by I. That is, this is the real part, and this is the imaginary part. This form of the complex number is called the rectangular form. So keep in mind that if you forgot this, rectangular form. This is very important to keep in mind. This complex number can be mapped to the two-dimensional Cartesian plane. Let's explain that. Over here is my vertical axis, and over here is my horizontal axis. On the horizontal axis, I will enter the real part of my complex number, and this is the notation for the real part. On the y-axis, I will enter the imaginary part of the complex number, and this is the notation for the imaginary part. A complex number is actually a point in this plane. For example, this point over here. And this point has the coordinates a and b. That is, the first coordinate is the real part, this distance over here, and another coordinate is the imaginary part, that is this distance over here. Over here we use the Cartesian coordinates or the rectangular coordinates to represent this point. However, we can also describe this point and its location in this complex plane by using polar coordinates. And the polar coordinates will actually motivate us to define the polar form of the complex number. So let's introduce polar coordinates. We can draw a vector starting from the origin 0 to this point, and here's the vector. The intensity or the length of this vector is denoted by r. Then, we need another coordinate, since this vector can rotate, and another coordinate is the angle that this vector creates with the real axis. And here's the angle. This angle is denoted by theta or theta. You can pronounce this Greek symbol by theta or theta. I will pronounce it as theta. Consequently, the point AB has the coordinates r and theta. What's the relation between A, B, R, and theta? Well, since this angle is 90 degrees, as well as this angle over here, we can see that A is r cosine or cos theta. And we can see that B is r sine theta. Consequently, if we substitute these expressions for a and b in the rectangular form of the complex number, that is, in this equation, we obtain z is equal to, instead of a, we will write r cosine theta. Then, instead of b, we will write r sine theta. And over here, we also need to add or to multiply this imaginary part by the imaginary unit I. Now, by using the Euler formula, we can represent actually this complex number also like this. Z is equal to R e to the power theta I. These two equations are actually equivalent and they represent the polar form of our complex number z. Let's explain this polar form. From this triangle over here, we can see that r can be expressed like this. The number r is called the modulus of the complex number z. In the literature, you will also read or you will also find that the modulus is called as magnitude or the absolute value of the complex number. These are the equivalent expressions. Then we have this angle theta. Theta is called the argument of our complex number z, and often you will see that theta is written as arg of z. In the literature, theta is also called as angle of z or phase of z, especially in control theory literature, theta is called as angle or phase of z. Unfortunately, there is no unique formula that covers all the cases for the angle theta or for the argument theta, and we need to consider case by case. Here is the first case. In this case, our complex number is in the first quadrant of the complex plane. That is, it's located over here. And in this case, a is positive and b is positive. And over here, we can use basic trigonometry. We can say that tan theta or tangent of theta is simply b over a. And from this equation, it follows that theta is inverse tangent or arctan of b over a. Arctan function is often also written like this as an inverse tan function. And we simply take b, divide by a, and compute inverse tangent to obtain theta. This is the first case. Here's the second case. This case corresponds to the case when our complex number is in the second quadrant. That is, it's over here. In this case, a is negative and b is positive. And here's how the angle theta looks. In this case, we need to apply this formula. We will have theta is equal to arctan of b over a plus pi, or in the equivalent form, theta is equal to inverse tangent b over a plus pi. Notice over here one thing. Since a is negative, this value over here will be negative. That is, this will be an angle that's negative. And once we add plus pi, the angle will be positive. This is because arctan function is in the interval from minus pi over 2 to pi over 2. And consequently, we will just take the angle pi and then subtract this angle over here. Here is the third case. This case corresponds when our complex number z is in the third quadrant. And here's how theta is defined. Notice over here that it's not a mistake if theta is defined like this, from this side. And in this case, theta will be actually negative. Theta is equal to arctan b over a minus pi, or inverse tangent of b over a minus pi. Notice over here, since b is negative and a negative, this whole term will be positive, and arctan will be a positive angle. That will be in the interval from 0 to pi over 2, and this complete angle over here will be negative, corresponding to this angle theta that's measured in the negative direction. That is, that's measured clockwise. And here's our fourth case. And the fourth case corresponds to the case when z is in the fourth quadrant, and the formulas are the same as in the case of the first quadrant. Namely, over here, we will simply have that tangent theta is b over a, and since b is negative over here, the angle will be negative and everything will be consistent, and consequently theta can be simply computed as arctan of b over a, or the inverse tangent of b over a. Okay, now we covered the computation of theta. Be careful over here and spend some time studying these four cases. Most of the students create errors over here. That is, they cannot accurately compute angle theta in this case and in this case. Let's solve the first problem. Here's our complex number. A is equal to square root of 3 over 2, and this is approximately 0.87, and b is equal to 1 over 2, and this is exactly 0.5. Let's sketch this complex number in the complex plane, and let's identify the case. Obviously, since both a and b are positive, we are considering the first case. Let's sketch it. For example, this will be a, 0.87, and b will be 0.2, and consequently our complex number is over here. In fact, it can be shown that this angle over here, theta, is actually 30 degrees. That is, I deliberately constructed this example in order to be able to verify our computations. So let's start. First of all, we need to compute r. r is equal to square root of a squared plus b squared. So let's see, what do we have over here? We have a square root of, let's write it down, square root of 3 over 2 squared plus 1 over 2 squared, and this becomes, let's write it down until the end, 3 over 4 plus 1 over 4, and this exactly becomes 1. That is the radius of our complex number, or the magnitude of our complex number, or equivalently the modulus of our complex number is 1. That is, this point over here is on the unit circle. How about theta? Angle theta is inverse tangent, or the arctan, of, let's see, imaginary over real. And over here we will have, let's see, we will have arctan of, let's see, we will have 1 over square root of 3. And it's easy to show that this angle is actually pi over 6. And consequently, the polar form of our complex number looks like this. Z is equal to r cosine theta plus r sine theta. Let me write it nicely. Multiplying I. So let's write it here. Z is 1 cosine pi over 6 plus 1 sine pi over 6 multiplying I. And we can write this number in the Euler form as 1 multiplying e to the power pi over 6 multiplying I. And that's it. In the second case, our complex number looks like this. Consequently, a is negative and equal to square root of 2 over 2 with the minus sign, and b is square root of 2 over 2. Let's sketch this complex number in the complex plane. Square root of 2 over 2 is approximately 0.71. Consequently, we will have a over here minus 0.71, and we will have b over here 0.71, and our complex number is located over here. And we immediately recognize that this is the second case, and the angle theta will be measured from here. And we need to apply the corresponding formula. First of all, let's compute r. r is the square root of a squared plus b squared. Let's substitute the value. We will have a square root of minus square root of 2 divided by 2 squared plus square root of 2 divided by 2 squared. And this becomes square root of, what do we have over here? We have 2 over 4 plus 2 over 4, and this becomes 1. Consequently, we see that the modulus is equal to 1. How about the angle theta? For the angle theta, we have to apply the corresponding case and the corresponding formula. We will have that theta is arctan of b over a plus pi. So let's substitute the value. We will have theta is arctan, b is square root of 2 divided by 2, and a is minus square root of 2 divided by 2. And let's close the parentheses, plus pi. Consequently, over here we will obtain arctan of minus 1 plus pi. Consequently, theta becomes arctan of minus 1 is actually minus pi over 4 plus pi, and this becomes, let's compute this nicely, 4 pi minus pi, and this becomes 3 over 4 multiplying pi. Good. That is, this angle, if we convert it to degrees, is 135 degrees. Good. Consequently, the polar form of our complex number looks like this. Z is equal to, let's immediately substitute the value, 1 multiplying cosine of 3 over 4 pi plus 1 multiplying sine 3 over 4 pi multiplying imaginary unit I, or we can also write this polar form in the so-called Euler form, and we will have 1 multiplying e to the power 3 over 4 pi multiplying I, and that's it. Here's our third problem. A is equal to minus 1 over 2, b is equal to minus square root of 3 over 2, and let's sketch this complex number. Obviously, this complex number is in the third quadrant, and we have a is minus 0.5, and b is approximately 0.87, since square root of 3 over 2 can be approximated by that number. So over here, let me just nicely sketch it, we'll have minus 0.87, and here's our complex number. It's located over here. Good. Let's now compute r. r is the square root of a squared plus b squared. Consequently, r is a square root of, let's see what we have. We have 1 over 4 plus 3 over 4. Over here, I'm immediately substituting the values, and we have 1. How about theta? For theta, we need to apply the corresponding formula. Since z is in this quadrant, theta will be measured from here. And our theta becomes arctan of b over a minus pi. And let's substitute the values. Theta becomes arctan b is square root of 3 over 2, and this should be divided by this. Don't forget the sign, right? We have a minus sign over here, and a is minus 1 over 2, and this becomes, let's see, arctan, and don't forget, yes, we shouldn't forget minus pi, and this further becomes theta is equal to arctan. Let's see, what do we have over here? 2 and 2 can be cancelled, and minus become plus, and we have the corresponding value that's equal to square root of 3. And over here we have minus pi. And let's see, what is the arctan of square root of 3? Arctan of square root of 3 is pi over 3, and consequently we have the theta is pi over 3 minus pi, and we will have over here 3 pi minus 3 pi, and this becomes minus 2 pi over 3. Good. Let's see this angle. This angle actually corresponds to the angle of minus 120 degrees. Consequently, the polar form of the complex number is r is 1, then we have cosine of theta, and the angle theta is minus 2 pi over 3. Then we have plus 1 sine of theta, and theta is minus 2 pi over 3, multiplying I. Or in the Euler form, we have z is equal to 1 e minus 2 pi over 3 multiplying I, and that's it. And here's our last problem. Over here, a is 1 over 2, b is minus square root of 3 over 2, and let's sketch this complex number. The real part is 0.5. The imaginary part is 0.87 approximately with the minus sign. That is, it's over here. Let me just write it nicely. Minus 0.87. And here's our complex number. The angle of theta is measured over here, or from the real part. Okay, so let's immediately compute r. r is square root of, let's see, a squared is 1 over 4, plus b squared is 3 over 4, plus sine, and this becomes 1. Next, we need to compute theta. This is the fourth case that's equal to the first case, and we can simply write theta is arctan of b over a, and this becomes arctan of b is minus square root of 3 over 2, and a is 1 over 2. And as the result, we obtain that theta is arctan. Let's see, what do we have over here? We have minus square root of 3. And consequently, theta is equal to minus pi over 3. And this is precisely the angle of 60 degrees with the minus sign. And this looks okay, and it fits the geometry represented over here. And finally, let's represent our number in the polar form. We will have r is 1 multiplying cosine of minus pi over 3 plus 1 multiplying sine of minus pi over 3. And we can write this number in the so-called Euler form. It is e, actually 1 multiplying e minus pi over 3 multiplying I. And that's it. Thanks for watching.